Welcome to The Explainer. Today we're diving into the beautiful, perfectly symmetrical relationship between electricity and magnetism. It's literally a journey that will take us from the tiny wires inside your everyday devices all the way to the massive power plants that light up the globe. Let's start with a really big question to frame our explainer today. Have you ever actually stopped to wonder how the power running your household appliances, like, say, the motor in your electric fan, is fundamentally the exact same force generating the electricity for the entire power grid? It all comes down to this incredible two-way street in physics, a perfectly reversible relationship in nature. Here's our roadmap for today. We'll start with how electricity creates magnetism. Then we'll look at building stronger magnets, the DC motor, how magnetism creates electricity, the AC generator, and finally, AC versus DC power. All right, let's jump right into section 1. Electricity creates magnetism. Picture this. It's 1820, and physicist Hans Ørsted makes this simple but honestly world-changing observation. Up until then, everyone thought electricity and magnetism were just completely separate things. But Ørsted notices that when he passes an electric current through a straight wire, it actually creates a magnetic field right around it. And we know this for sure because it physically deflected a compass needle sitting nearby. You turn the current on, the needle moves. You reverse the current, and boom, the needle deflects in the exact opposite direction. So, to make sense of this invisible force spinning around the wire, physicists use these really handy physical shortcuts. We're going to start with the foundational right-hand thumb rule. It lets us instantly visualize the shape and direction of that magnetic field just by looking at which way the electricity is flowing. Imagine holding that current-carrying wire right in your right hand. Just point your thumb upward in the direction the current is flowing. When you do that, the natural curl of your fingers maps out the exact circular magnetic field wrapping around the wire. It's this elegant, concentric circle of invisible force totally dictated by the flow of electricity. Moving right along to section 2, building stronger magnets. Okay, so a single straight wire makes a pretty weak magnetic field, but engineers quickly figured out a way to amplify it and create a highly controllable tool. If you take that straight wire and just bend it into a single loop, you start to concentrate those magnetic field lines right through the center. But the real magic? That happens when you tightly wind the wire into a long cylindrical coil, which we call a solenoid. Those individual magnetic loops combine. The field lines straighten out perfectly inside the coil and curve right around the outside. It acts exactly like a traditional permanent bar magnet, but with one massive advantage. That huge advantage is that these electromagnets are completely customizable. We aren't stuck with just one fixed strength. We can literally crank up their power on demand. How? Well, 3 simple ways. You can add more turns of wire to the coil, you can push more electrical current through the circuit, or you can drop a piece of soft iron, a core, right into the center of the coil. That soft iron dramatically multiplies the magnetic permeability. So we get this ultra-strong magnet that we can just turn on and off with a switch. How cool is that? Which brings us to section 3, the DC motor. Now that we've got this supercharged, controllable magnet, we can actually use it to do physical work. But before we build a motor to do that, we need one more hand rule to understand the mechanics. Meet Fleming's left-hand rule. Basically, if you put a wire carrying a current into an existing magnetic field, that wire is going to experience a physical force. It's going to move. Fleming's rule tells us exactly which way. Stretch out your left forefinger for the magnetic field, your central finger for the current, and your thumb will point perfectly in the direction of the resulting motion. Applying that rule to a simple DC motor, we've got an armature, that's the rectangular coil of wire, placed horizontally inside a strong horseshoe magnet. Notice how the ends of that coil are hooked up to a very specific, absolutely crucial part called a split ring commutator, which rubs against stationary carbon brushes connected to a battery. So here's how it all comes to life. First, current flows from the battery into the rectangular coil. Thanks to Fleming's left-hand rule, one side of the coil gets pushed up and the other side gets pushed down. It starts to spin. But hold on, if it spun halfway around, the forces would just trap it there, right? That's where step 2 kicks in. The split ring commutator is the real mechanical genius here. As the coil hits that vertical position, the split completely breaks the circuit for just a fraction of a second. Momentum carries it right past the gap. And in step 3, the halves of the split ring actually swap contact brushes. This physically reverses the electric current inside the coil every half turn. That ingenious little flip ensures the upward force stays on the left and the downward force stays on the right, meaning the coil just keeps spinning smoothly in one continuous direction. We literally just turned electrical energy into mechanical motion. So, we've just seen electricity turn into motion. And that brings us to the ultimate, perfectly symmetrical question that completely flips the script of physics. If sending electricity through a wire creates a magnetic field, can moving a magnetic field across a wire somehow create electricity? Let's find out in Section 4. Magnetism creates electricity. Back in the 1830s, the brilliant Michael Faraday set out to prove that this two-way street of nature was actually real. In his incredibly elegant experiments, he attached a wire coil to a sensitive galvanometer, which is just a meter that detects electrical current. Note that there is absolutely no battery in this circuit. Zero. But Faraday showed that simply plunging a stationary permanent magnet into the hollow coil physically forces a brand new electric current to flow through the wires. The needle jumped. And if you pull the magnet back out, the current flows in the exact opposite direction. Physicists call this process electromagnetic induction. And the absolutely crucial takeaway here is the word change. If you just leave the magnet sitting inside the coil doing nothing, it does absolutely nothing. It's the relative motion, the changing magnetic flux slicing through the stationary wires over time, that does the mechanical work of actually generating electricity. Basically, no motion, no power. This leads us perfectly to Section 5, the AC generator. Building directly on Faraday's incredible discovery, we get to the heavy-duty machines that literally power our modern world, the AC generator. Now, notice how visually similar this generator is to the DC motor we just looked at. It has the same strong field magnets and the same central rotating armature coil. But look really closely at the connections on the axle. Instead of a single split ring designed to reverse current, the AC generator uses two distinct continuous slip rings. Each end of the coil wire is permanently bonded to its own dedicated ring. Here's how it operates, basically in reverse of a motor. First, an outside force, think of a spinning wind turbine or a steam engine, provides mechanical energy to physically crank that coil around inside the magnetic field. Second, as the coil continuously rotates, it constantly changes the magnetic flux slicing through it, and that induces an electromotive force. Finally, because those two slip rings are continuous, they don't correct the current's direction like a commutator does. Instead, they output the raw induced current, which naturally pushes and pulls, reversing its direction perfectly every single half rotation. And there you have it. We are outputting alternating current. Let's wrap things up in Section 6, AC versus DC power. We've explored this amazing symmetry between generating motion and generating power. But we really need to clearly compare the two distinct types of electrical current these systems use. Bringing it all together, on one side, the DC motor takes electrical energy, uses split rings, and creates mechanical motion. Perfectly mirroring this, the AC generator takes mechanical motion, uses continuous slip rings, and spins out electrical energy. They really are just two sides of the exact same electromagnetic coin. But the outputs are fundamentally different. Direct current, or DC, the stuff that powers your phone and comes from batteries, flows continuously in one single flat direction. Alternating current, or AC, which is supplied by those massive generators to your house outlets, acts like a wave. It continuously changes magnitude and periodically reverses its direction. In fact, it swings back and forth 50 times every single second in many parts of the world. This symmetrical dance of physics, turning motion into electricity and electricity back into motion, is literally the heartbeat of modern society. We've mastered the two-way street. But understanding how we generate alternating current leaves us with one final, pretty provocative question. If AC is so straightforward to produce at a power plant, what actually limits how far this invisible power can travel? How do we push this reversing electrical current across thousands of miles of wire without losing all that energy to heat along the way? Think about that the next time you flip a light switch. Thanks so much for joining me on this explainer, and keep questioning the incredible world around you.